For the first time in more than 150 million years, nothing large is walking through this forest. Nothing you would feel through the soles of your feet. Nothing tall enough to pull leaves down from above your head. The heaviest animal moving between the palms weighs about as much as a big dog, and it has almost nothing to be afraid of, because nowhere on this continent is there a land hunter built to bring it down. The forest is warm, wet, loud with insects, and empty in a way no forest has been in a very long time. 65 million years ago, 1 million years after the asteroid. The sky is clear, the trees are back, and the planet is running with most of its biggest jobs unfilled. Under the leaf litter, a few meters down, there is a band of clay thinner than your finger. It carries iridium, an element that is scarce in Earth's crust and common in asteroids, and small beads of glass that were once rock thrown into the sky and cooled on the way down. Above it sits 1 million years of sediment. In a few places you can put one hand on the layer where the old world ends, and the other on the layer where this one is already running. The opening act, the part that gets filmed, was over almost immediately. Rock thrown out by the impact came back down through the atmosphere and heated the sky. Dust and sulfur from the target rock cut the sunlight, and the models put the shutdown of photosynthesis somewhere between a few months and a couple of years, with the numbers depending on assumptions nobody can test directly. Then the dust settled out, and the sun came back to a surface with almost nothing standing on it. Everything after that is the slow part, and the slow part is where this planet was actually rebuilt. 1 million years is a hard number to hold on to. Everything humans have ever written down, from the first clay tablets to this sentence, covers roughly 5,000 years. Lay 200 of those end to end, and you have the gap between that clay band and the forest floor above it. The recovery in this video is not a scene. It is a stretch of time long enough to swallow all of recorded history 200 times over, and it still counts as fast. The first thing to cover the ground afterward was not a tree. Boundary cores from several continents show the pollen handing over to a layer stuffed with fern spores and almost nothing else. Ferns are what grows on fresh volcanic ash today. The spores arrive on the wind, they ask nearly nothing of the soil, and they hold bare ground until something taller can take it. That phase runs on the order of a few thousand years, which in this hillside is a smear you could cover with a coin. The plants that came back mostly did not arrive from anywhere. They were already in the ground. Seeds sitting in the soil, roots and rhizomes waiting under the surface, and buried stems that could push up a new shoot once the light returned. That is one of the quieter reasons the land recovered at all. A forest can be flattened and still hold most of its next generation underground. At some boundary sites, there is also a spike in fungal spores just above the clay, which has been read as a stretch when the main thing on the menu was dead wood. How widespread that phase really was is still argued over. The forest that came after the ferns is green, thick in patches, and monotonous. Palms dominate the plant record of the Denver Basin through this stretch, and the species count is a fraction of what grew on the same ground in the last age of the dinosaurs. Whole families of flowering plants drop out and never come back. What is left grows fast, seeds hard, and tolerates open dirt. The air would throw you before the plants did. It is warm and heavy with water. Leaf shapes from these layers, the smooth margins and the long drip tips, point to a climate closer to the modern Gulf Coast than to the dry, high plains sitting on that spot now. Denver today is a mile up, brown by August, cold at night. Here the ground never really dries out, and there is no season that could hurt you. West of this forest, the ground is going up. The mountain building that raises the Front Range is running through exactly this stretch of time, and the rivers coming off those young slopes carry sand and mud east into the basin, spreading it in sheets across the floodplain. That is the only reason any of this is readable now. Bones get buried fast, layers stack in order, and a hillside east of a modern city ends up holding a legible record of one of the strangest million years in the history of land life. The leaves carry a second signal. Paleobotanists count the kinds of damage insects leave behind: chewed margins, mines tunneled between the leaf surfaces, galls, punctures along the veins. In early Paleocene rocks in North Dakota and Wyoming, that variety collapses and stays low for a long time. Insects that fed on one kind of plant went out with their plant. What is chewing here now are generalists working a food web that lost most of its connections. No animal in this forest can knock a mature tree over. For tens of millions of years, animals weighing several tons had shoved through vegetation, stripped branches at heights nothing here can reach, and flattened seedlings by accident. That pressure is gone, and the fossil forests of Colombia suggest it mattered more than anyone expected. Before the impact, the forests there were open, full of conifers and ferns, with light reaching the floor. Afterward, they close in, dense, layered, dominated by flowering plants, dark at the base. The structure we think of as a normal rainforest may be what grows when the animals that used to break it open are no longer there. In the Hell Creek country of Montana, one survey of the boundary found roughly 9 in 10 freshwater vertebrate species carrying on into the Paleocene. For the animals living on land beside those same rivers, the figure was closer to 1 in 10. Same region, same rock, same event, and an order of magnitude between the two outcomes. The difference is where the energy came from. A forest runs on sunlight hitting leaves. Block the light for a season or two, and everything stacked above those leaves comes apart. A river runs on dead plant material washed in from the banks, broken down by microbes and insects, passed up to fish, and from there to turtles and crocodile relatives. That chain barely notices the sky. Which is why the rivers of this world look almost normal, and why they are the eeriest thing in it. Soft-shelled turtles on the sandbars, gars holding in the current, a crocodile relative on the bank that is, at several meters, the largest predator on the continent. Beside it, something that looks like a slim crocodile with a long, thin snout, and is not a crocodile at all, a champsosaur, from a reptile line that had been in these rivers long before the impact and will keep going deep into the Paleocene. On land, the biggest hunter might weigh a few kilograms. In the water, the old order never fell. The birds that were most common in the Cretaceous had claws on their wings and teeth in their beaks. Not one of those lineages appears above the clay. What crossed the boundary were a few branches of the group that holds everything with feathers today, and the survivors seemed to share a habit. They lived on the ground or nested there. That fits a world where the forests burned and then took centuries to grow back. If your life depended on a canopy, for a while there was no canopy. Every duck, hawk, and songbird alive now came through that gate, and the fossil record of the crossing is thin enough that people still argue about the order of the branching. If getting dropped into versions of this planet you would not recognize is your kind of thing, subscribe and stick around. There are plenty of them left. Mammals did not inherit an empty world and grow into it right away. Before the impact, the largest of them in North America topped out at a few kilograms, cat-sized at the upper end, and for the first stretch after the boundary, they got smaller still. The place to watch what happened next is a set of low hills east of Denver called Corral Bluffs, where skulls sit inside stone concretions that a field team eventually learned to spot by the shape and color of the rock. Layer by layer, the sequence reads like a growth chart. In the first 100,000 years, the heaviest mammals in the basin come in around 0.5 kilogram, roughly a rat. By 300,000 years, the top end is near 6 kilograms, and palms are taking over the forest. By 700,000, it is somewhere close to 50. That last one is the animal from the opening, blunt-toothed, built low to the ground, from a family of early hoofed mammals with no living descendants. Body mass for fossils like these gets estimated from teeth and limb bones, so the number carries a real margin. Different methods can move an animal like that by 10 or 15 kilograms in either direction. The shape of the curve is what holds up. Species counts climb with it. Through that same interval, the number of mammal kinds found in the basin multiplies several times over, which is the part that actually matters. Not one animal getting heavier, but a whole group filling out. Those dates are not eyeballed off the outcrop. Ash beds inside the sequence carry crystals that can be dated by the decay of potassium into argon, and the same layers record reversals of Earth's magnetic field that are numbered worldwide. 2 clocks, checked against each other, running through one hillside. Around that same 700,000 year mark, the first legumes turn up in the rock. Beans, broadly speaking. Legume leaves and seeds carry more nitrogen than most plant tissue, which is more protein per mouthful for anything able to process them. Bigger bodies need richer food, and here is richer food showing up in the same layers as the bigger bodies. It is a correlation from a single basin, and the team that published it said as much. Whether the plants pulled the animals up in size, or the animals spread the plants, or a warming climate did both, is not settled. Not every branch of the mammal family got the same deal. Relatives of modern marsupials had been everywhere in the Cretaceous of North America, and at the boundary they were cut down harder than almost any other mammal group on the continent. They never recover here. Their surviving relatives make a living in the south, which is why the marsupials of the modern world are in Australia and South America instead of Montana. The animals climbing the size curve in Colorado come from the other branch, the one that includes us, and part of the room they had was room their competition left behind. Overhead, in the branches, there is an animal the size of a mouse with teeth suited to fruit and insects. Purgatorius. It turns up in rocks laid down within a couple of 100,000 years of the impact, and it is usually described as the earliest known relative of primates, although that placement is genuinely contested, and some analyses push it outside the group altogether. We know it from teeth, mostly, plus a handful of ankle bones with joints loose enough to grip a round branch. That is the honest limit of what the fossils say. Nobody has seen its face, its fur, or one thing it ever did. The most common mammals down in the understory belong to a group that eventually lost everything. Multituberculates, named for the rows of bumps on their grinding teeth, had been around since the Jurassic, and they came through the extinction better than almost anyone. They gnaw, dig, climb, eat seeds, and breed fast, which is roughly the job rodents do now. Rodents do not exist yet. When they finally appear and spread, the multituberculates begin a slide that ends with the group gone entirely. For the moment, they own the floor of this forest. There are no cats here, no dogs, no bears, no weasels. None of those lineages exists. Away from the water, a 50-kilogram plant eater can live its whole life without a serious predator above it, and its body says so. heavy, unhurried, built to push through vegetation rather than to outrun anything.
Colorado is one warm basin on a planet with no permanent ice at either pole. Forests grow within a few degrees of both, and they handle 3 months of unbroken darkness by dropping their leaves and shutting down until the light comes back. Antarctica is green and still joined to South America at one end and Australia at the other, so the cold current that will eventually wrap around it and freeze it does not exist yet. India is an island in open ocean, drifting north toward the collision that will raise the Himalayas. Europe is a scatter of islands in a shallow sea. The Atlantic is open but narrower, and across the north, plants and animals are still moving between North America and Europe. The eruptions on the far side of that world did not stop at the boundary. In what is now Western India, the lava fields kept building for hundreds of thousands of years afterward, venting gas along with the rock. And how much of the extinction belongs to the asteroid and how much to the volcanism is still one of the sharper disagreements in the field. Carbon dioxide stays high. Over the next few million years, the climate gets warmer, not cooler. At sea, the boundary is even harder to miss. Below it, chalk built from the shells of single-celled plankton. Above it, a layer where those shells nearly vanish, with something like 3/4 of plankton species dropping out of the record. Ammonites, after more than 300 million years, are simply absent. The large marine reptiles are gone. Surface water and deep water end up carrying almost the same carbon signature, which is what happens when very little living material is sinking from above. That state takes hundreds of thousands of years to fade, and full plankton diversity takes millions. Sharks come through it thinned, so do the bony fish, and they end up running the modern ocean. And the recovery is not one story told at the same speed everywhere. South America is an island continent at this point, cut off from the north, and whatever is happening there is happening on its own terms, with its own hoofed groups that will never leave the continent, and, later, its own giant flightless birds. Africa is isolated too. Most of what anyone can say in detail about this million years comes from a narrow strip of rock in western North America, because that is where the layers are exposed, dated, and picked over by more than a century of fieldwork. The map of what we know is not the map of what happened. We can date the layers, count the pollen, measure the isotopes, and weigh the bones. We cannot tell you what color any of these animals were. We do not know what most of them sounded like, how they raised their young, or whether the plant eaters moved in groups. Past size and shape, most of what you see in a reconstruction of this world is inference, and some of it is decoration. Recovery also ran on different clocks in different places. Corral Bluffs is one basin on one continent. In the Colombian record, plant diversity takes something like 6 million years to climb back, which is 6 times the entire span of this video. A million years in, this planet is not damaged and waiting. It is rebuilt and running on a smaller cast, with several of the largest jobs still open and a plant community that has already reorganized itself around who is not there. The band of clay under the forest floor is a few centimeters thick. Everything else, the ferns, the palms, the ground birds, the animals climbing from 0.5 kilogram to 50, sits in a wall of sandstone you could stand beside and measure with your arms out. And somewhere inside it, 30 grams of mouse-sized animal is holding onto a branch with feet that can already grip. Tell me which vanished Earth you want next. Forested Antarctica with its 3-month night, or Beringia, the drowned continent people once walked across? Put it in the comments and I will start digging. Subscribe if you want to be standing there when I do.